We are now going to have a look at a few different ways in which we calculate the molar heat of combustion and other variables associated with the heat of combustion. In practice question 1, we are being asked to calculate the heat of combustion per gram and per mole of methanol considering the following data. The first step in the process is to calculate the change in enthalpy. So that's using our delta H is equal to negative MCAT, where the mass of water for this example was 100 grams. The specific heat capacity of water is constant at 4.18 joules per gram per degree Celsius. And delta T, where the change in temperature is equal to the final temperature minus the initial. So in this particular instance, the change in temperature was 10 degrees Celsius. So we substitute our values into the equation, and that gives us a total change in enthalpy of negative 4,180 joules. Now, whenever we're dealing with heat of combustion, we're always going to convert that into kilojoules. Note the negative sign, which is showing that this is an exothermic reaction. Then we need to calculate the heat released per gram. So if we looked at our data, the methanol mass the change in methanol mass can be calculated using the initial minus the final, where in this particular instance, the initial will be always greater than the final mass. So 20 minus 19.79 gives us total mass of 0.21 grams combusted. So what we want to do is divide the change in enthalpy by the mass that was combusted. So in this particular instance, it's as simple as negative 4.18 divided by 0.21, which gives us negative 19.90 kilojoules per gram released. If we want to calculate the heat released per mole, we then have to find out the moles of methanol. So on the side here, you can see the number of moles is equal to mass over molar mass. So in this particular instance, we need to know the formula of methanol in order to work out its molar mass. So the formula for methanol is CH3OH. So using our periodic table, we've worked out that the molar mass is 32.042. So we've divided 0.21 by its molar mass, and that's given us a number of moles of 0.00655. And we don't round until the end, of course. So in order to work out the molar heat of combustion, which is shown here by the formula delta H subscript C, so that's a little notation to know, that is equal to the change in enthalpy converted to kilojoules divided by the number of moles. So here we've got it here. So that's equivalent to negative 4.18 divided by the number of moles that we found out earlier, and that's equal to a total molar heat of combustion of negative 637.79 kilojoules per mole. So that's the number of kilojoules released per mole of methanol combusted according to our data. Here's an alternative way to calculate the heat released per mole if we already have the heat released per gram. We know the molar mass of methanol is 32.042 grams per mole. We know that the heat released per gram was negative 19.90 kilojoules per gram. So what we can actually do there is we can if we know that this is per 1 gram, the heat released per 1 gram, and we know that there are 32.042 grams in 1 mole, what we can do with the kilojoules per mole, per gram, is we can times that by the molar mass to get the molar heat of combustion. So in this instance, what we're doing is we're timesing the heat of combustion per gram, timesing it by the molar mass, and if you notice that the value that we get is negative 637.79 kilojoules per mole, which is exactly the same as the value that we calculated earlier. So you can use either of the two methods, keeping in mind that this alternative method is only when you've calculated the heat of combustion per gram initially, and then you can work to moles. For homework, I got you to compare to the standard. So having a look at this particular example, the standard heat of combustion for methanol is actually 726 kilojoules of heat release per mole, denoted by the negative sign. However, based on our experimental data, the calculated value was actually negative 637.79 kilojoules per mole. So what we're noticing, and I hope that's what you noticed for homework as well, is that the experimental data is always showing a value lower than that of the standard. So we just have a chat about that for a moment. So we've got to think about what were the conditions of the experiment that allowed some of that heat not to be transferred to the water. So where did that heat go that didn't allow it to be fully absorbed by the water? We talked about in class the heat being liberated or lost to the surroundings. So you've got to think about those factors when you're looking at your experimental data. Let's have a look at another question, a little bit different in terms of what we're calculating. In this instance, we're given the molar heat of combustion of pentanol, or 1 pentanol, which is 2,800 kilojoules per mole. A quantity of pentanol was combusted, and that generated 118 kilojoules of heat. So what we're being asked to do is calculate the mass of pentanol combusted. So in this instance, we can actually calculate the moles using the formula. The molar heat of combustion is equal to change in enthalpy divided by moles. We simply need to rearrange the equation, which becomes change in enthalpy divided by the molar heat of combustion. So if we substitute our values in, 118 divided by 2,800, and that gives us the total number of moles of pentanol combusted. So what we simply have to do is convert the moles into mass. So we know mass is equal to number of moles times by the molar mass. And we again need to know the formula for pentanol, which in this particular instance, or for pentanol always, is C5H11OH. So we need to know our generic formula for alkanols when we're working with these sorts of calculations. So the mass therefore is equal to 0.042 ... by 88.146, which is the molar mass for pentanol. That gives us a total mass combusted of 3.71 grams. So it's just a different variable that's being asked of you to calculate. Let's have a look at another type of question. Practice question 3. The molar heat of combustion of ethanol is given as 1,367 kilojoules per mole. If you've noticed in practice question 2 and practice question 3, there is no negative sign for the molar heat of combustion as a standard value. Now that's simply because we always assume, or we don't assume, we know that combustion is exothermic. So the chemists have decided that there's no reason for them to always put the negative, because we know when we're talking heat of combustion, it is always going to be heat released, so we assume the negative, okay? Assuming no heat losses to the surroundings, what mass of ethanol must be combusted to raise the temperature of 0.250 kilograms of water from 20 degrees to 60 degrees? So it's again asking mass, but now we're actually not given the change in enthalpy, we've got to calculate it ourselves. So there it is. We look at our data on the side here, and we've got a change of temperature of 40 degrees. So we substitute all of these values into our equation, 250 by 4.18 by 40, and that gives us a total heat generated by the reaction or released of negative 41.8 kilojoules when I've converted from joules to kilojoules, as I always must. Then I can calculate the number of moles combusted using the formula. Delta H, molar heat of combustion, equals to change of enthalpy divided by moles. Rearrange to make moles the subject of the equation, and it's simply 41.8 divided by 1,367, which gives us a total moles of 0.03057. And then I simply have to rearrange the equation for mass, which is equal to number of moles times molar mass, times the moles that I got of ethanol, knowing the formula for ethanol, which is C2H5OH. That gives us a molar mass of 46.068, and that gives us a total mass combusted of ethanol of 1.408 grams. Last type of question, which we're going to have a look at in this particular video, is looking at a student completing an experiment to determine the amount of energy absorbed by a volume of water. So it's not telling us about any particular alcohol or fuel that was combusted. It's just telling us this was absorbed by the volume of water. So note that down. The following data was recorded. And then what we're being asked to do is calculate the initial temperature of the water. So because we're being asked to calculate the heat absorbed by the water, it's actually not a delta H question because we're not looking at a change in enthalpy in terms of a chemical reaction. We're just looking simply at the amount of energy absorbed by the water. So we're using Q is equal to MCAT in this particular instance, where Q represents the heat added to the system. We use this last term as well. So we actually want to see the temperature final minus the temperature initial in the equation because we know we're trying to ascertain the initial temperature. If we rearrange the equation once again, then we want to make the temperature the subject, so TF minus TI, which is equal to Q over MC. Here's our data. So we've been given a change in enthalpy in kilojoules. So because we need to convert, in this particular instance, we need to convert from kilojoules to joules, okay? Because delta H or Q, we always work in joules when we're talking about the MCAT equation. So we times that by 1,000, gives us 21,300 joules. The mass of water from our data can be calculated using the mass of the beaker plus the water minus the mass of the beaker alone, which is 120.5 grams. Specific heat capacity of water remains the same, obviously. And our change in temperature is 68 minus T initial, which is what we're trying to work out. Then we substitute the values into the equation. There it is there. So 68 minus Ti is equal to 21,300 over 120.5 by 4.18. And that's going to give us a value of 68 minus Ti, which is equal to 42.28. And then all we need to do is a little bit of simple algebra. So we're going to move the 68 over to the right-hand side of the equation. So that's going to give us negative temperature initial is equal to negative 25.7. And then I haven't changed that at the bottom there, but that should be the initial temperature is equal to 25.71, not negative 25.71. And that brings us to the end of our molar heat of combustion calculation session. So have a go at doing the examples that I'm leaving you in class today. And I hope this video has helped you work out how to do all of these sorts of equations.